This is the example video for differential equations. Our first equation is a pure time differential equation. We have dy dx equals 1 over x, and we have initial condition y0 equals 0 when x0 equals 1, and we want to find y of x. So we want to get y by itself and x by itself, so we multiply both sides by x, we multiply both sides by dx. We get dy equals 1 over x dx, and then we integrate both sides. So we have the integral of dy equals the integral of 1 over x dx. The integral of dy is just y plus c. The integral of 1 over x is ln absolute value of x plus c, and since there's a plus c on both sides, we can combine them into one constant, and we can just call that c, because two constants subtracted by each other is just a constant. And this is y of x equals ln absolute value of x plus c. And now we plug in our initial condition. So y0 will equal ln of x0 plus c. y0 is 0, and x0 is 1. So ln of 1 is 0, so c equals 0. So y of x equals ln absolute value of x plus 0. We don't need to write that, so our solution is y of x equals ln of absolute value of x. So our second example is dn dt equals 5 minus n, and we have an initial condition n of 2 equals 3. This is an autonomous differential equation because everything on the right hand side is in terms of n, the dependent variable. There's no t's on this side, so we use the same procedure and we multiply both sides by dt, and then we divide both sides by 5 minus n. So now we have all the n's on one side and then all the t's on the other side, and then we integrate both sides. So the integral of 1 over 5 minus n dn equals the integral of dt. We use a u substitution here. U equals 5 minus n, du equals negative dn. We get the integral of 1 over u times the negative du, and this equals the integral of dt, which is just t plus c. And we pull this negative out, we have the integral of u to the negative 1 du equals t plus c. Integral of u to the negative 1 is just ln u, absolute value. We don't need to write a plus c on this side because we have one on that side. Now, if we put the negative over onto the other side, let's substitute u back in. So we have negative ln of 5 minus n equals t plus c, and right off the bat we can use our initial condition. N of 2 equals 3, so wherever we see n, we're going to put in a 3, and wherever we see our t, we're going to put in 2. Simplify this, we have ln 2 equals 2 plus c. So c must equal negative ln absolute value of 2 minus 2. And now we go back to our equation here, and we plug in our c as negative ln of 2. We can drop the absolute value because 2 is a positive number, minus 2. We exponentiate both sides. Or actually, let's multiply both sides by negative 1. And we'll get ln absolute value of 5 minus n equals negative t plus ln 2 plus 2. We exponentiate both sides. E and the ln's cancel because they're inverses, and we get 5 minus n equals e to the negative, and this should be absolute value, e to the negative t plus ln 2 plus 2. And if we use our exponent rules, we can make this e to the ln 2 times e to the 2 minus t. E to the ln 2 is just 2. So on the right side we have 2 times e to the 2 minus t. And on this side we have absolute value of 5 minus n. And to check if this is a positive or negative value, we check our initial condition really quick. If we put in 2 here, or we put in 3 here, we put in 2 here for t, we get absolute value of 2 equals 2, and if we take the positive value of this, the equation holds, so we can drop the absolute value and leave it positive. And now we solve for n, and n of t is 5 minus 2 times e to the 2 minus t. And that is our solution. So our third example is the rate of change of r with respect to t equals r times e to the negative t. And we have our initial condition r sub 0 equals 1 when t sub 0 equals 0. Now I'm going to show you a different way to deal with the initial conditions here, but let's separate this equation first. So if we divide both sides by r, multiply both sides by t, or dt, we get 1 over r dr equals e to the negative t dt. And now we can integrate both sides. But instead of doing an indefinite integral like we've been doing before, we can integrate from our initial values, r0 and t0, to our final values, r and t. So now instead of indefinite integrals, we have definite integrals. The integral of 1 over r is ln absolute value of r from r to r0. Integral of e to the negative t is negative e to the negative t from t to t0. If we evaluate this integral, we get ln absolute value of r minus ln absolute value of r0. And this should equal negative e to the negative t minus negative e to the negative t0. If we use log rules, we can combine this into ln r over r0, and this should equal negative e to the negative t plus e to the negative t0. Now we can check what our r0 and t0 are. r0 is 1, and t0 is 0. So ln of r over 1 is just ln absolute value of r, and e to the 0 is 1. Now if we exponentiate both sides, we get absolute value of r equals e to the negative e to the negative t plus 1. And to see which, if we take the positive or negative value, we just check our initial conditions really quick. And when r is r0, or 1, this should be e to the negative e to the negative e to the negative e0, which is t0, which is 0, plus 1. And this should be e to the negative 1 plus 1, e to the 0, which is 1, so we take the positive absolute value. So r of t is equal to e to the negative e to the negative t plus 1. And we can write this as the exponential function, exponential of e to the negative t plus 1. And that is our solution.